Hello everyone. In today's video, I wanted to introduce you to a nice interactive tool that allows you to demonstrate and explore concepts behind correlation and regression. So this Correlation Explorer allows the user to specify with the left-hand side of the panel different relationships between the variables x and y, what level of correlation they would like to see, and given sample sizes. By toggling this slider, the user can increase the correlation and see what data points will look like with approximately that level of correlation. Similarly, the user can toggle the sample size and see what happens as they increase the number of observations with different levels of correlation, and explore what those patterns will look like when there is strong positive, strong negative, or no correlation between the variables x and y. Another useful feature of this tool is the toggle button at the top that shows the regression equation. By turning that on, it overlays the regression equation on the scatter plot, and it also shows you the intercept and slope coefficients that are computed for those regression coefficients. This scenario drop-down menu allows you to explore some of the different options that might be encountered. For example, a nonlinear relationship between two variables x and y demonstrates that x and y have a very strong association, but as far as the correlation coefficient goes, it's going to miss that correlation and give us something close to 0. And again, this can be modified in terms of the sample size and see how that affects the measures of correlation. Another interesting option here is the restricted range effect, where I might have very correlated observations x and y. In fact, let's change that correlation to be something very strong. But if I restrict how much of the domain is considered for my data set, typically it has the effect of weakening the observed correlation between those variables. So down here I see that the true correlation coefficient on all of the data points, those that are gray and those that are outside of the restricted range, is 0.83, very strong actually. But the restricted range of the data points within that window is 0.438. The effect of an extreme outlier can be explored as well. Notice that these data are generated as being uncorrelated, and I have an extreme outlier here that shows the regression line gets pulled up, but my estimated correlation coefficient is 0.39. It's not close to 0. This tool calculates the correlation with and without the outlier so you can see the effect. You can also explore what happens as you increase or decrease the sample size and see that the effect of the outlier becomes decreased in the presence of more data. However, with a smaller sample size, the effect of that outlier becomes more and more extreme in regards to the sample correlation coefficient. These last three scenarios have to do with Simpson's paradox. This is essentially having two groups that are represented in the data set, and in this scenario, the groups themselves are within a group, the x and y variables are uncorrelated. But if I don't recognize that I have two groups, it may be that I get the incorrect view of the sample correlation coefficient. For example, this group is uncorrelated with x and y, this group is uncorrelated with x and y, but combining those two groups, I get a correlation coefficient of 0.96, which shows a very strong correlation. And this effect of not accounting for the groups within a data set can show some very surprising results, where we go from being uncorrelated within a group to even having a negative correlation within each of those groups, but then considered collectively, I get a positive correlation. And then the opposite is true, where maybe I have a positive correlation within each group, and taken collectively, I get a negative correlation. So these are all examples of what is referred to as Simpson's paradox. A nice feature of this tool is the custom data input window. Users can copy and paste data from other sources directly into this window separated by spaces. The first column will correspond to the X variable, in this case BMI, and the second column will correspond to the Y variable, in my case systolic blood pressure. Clicking Plot Data will plot these data in a scatter plot, and you can see the overlaying regression line along with the calculated sample correlation coefficient and the estimated regression equation. Users can view statistical details by clicking on this drop-down option. You can see the mean of X and Y, variance of X and Y, and the covariance of X and Y. In the calculation steps, the formulas that users will be familiar with or introduced to in an introductory statistics course are displayed and also calculated for the given data set. This can be a really helpful tool for users that are trying to replicate calculations elsewhere. With data in the custom data input window, another option for obtaining a predicted value of Y from a given value of X appears. For instance, I can calculate the predicted value of systolic blood pressure when BMI is 20. It is put on the scatter plot as a red dot, and hovering over it tells me that the predicted systolic blood pressure is 113.13. I can include multiple predicted values by separating them simply using a comma, and it will overlay each of those on the scatter plot. Again, hovering over them shows me the predicted value of Y at each of those X values. So this completes my introduction to what can be a helpful tool, especially when you're introducing students to the concepts of correlation and regression for the first time.